In Poisson's discovery of 1837, we had found, accidentally as it were, a curious little approximation to the binomial. Though, as we saw in the century and a half that followed, this discovery had entrancing and unexpected effects. And now, through another venerable artifact, the method of inclusion and exclusion, we find the binomial reappearing again, accidentally, serendipitously. Are these discoveries then connected, the idea of the binomial to the Poisson? Is it part of a deeper phenomenon? Or was it just mere serendipity? Well, surely we can't simply dismiss it as accidental without further investigation. And this line of thought is going to lead us to the discovery of a delicate and beautiful Poisson sieve. To understand where this arises, we should go back and review what we had discovered in the case of the binomial. So the question now is, what is at the heart of this Poisson approximation for the binomial? Well, let's start with the simplest setting for inclusion and exclusion, where we have a collection of independent events, and where every event has the same probability, p. We promptly introduce the idea of an indicator which captures whenever an event occurs. And our discovery was that the inclusion-exclusion formula promptly drops the binomial distribution into our laps. The number of occurrences of these independent events is governed by the binomial distribution with parameters n and p. Now, whence the Poisson distribution? Where does it arise? Well, of course, we got to the Poisson through the binomial in the province of rare events. So let's consider a situation where the events a1 through an, the bad events as it were, are rare. What does that mean? It means the chance of occurrence of any one of them, p, is small. We're going to look in an asymptotic regime where n, the number of events, is quite large. So we have a lot of bad events, each with a small probability of occurrence, and the expected number of the events that occur is a moderate number, n times p, that we call lambda. Now let us step through the inclusion-exclusion argument again very quickly this time to get a feeling for why things worked the way they did. So we begin with the inclusion-exclusion sums. In this case, these sums are simple to characterize because the events are independent, and immediately we get a binomial coefficient times the power of p. Well, we simplify the binomial coefficient, write it out. We find a falling factorial in the numerator, a factorial in the denominator. But the falling factorial has got k plus j terms, each of which is approximately n. Remember, n is large, and we'll want to look in a regime where k is relatively small compared to n. And in this case, we discover that these inclusion-exclusion sums appear to be of the form of a power of a fixed parameter lambda divided by a factorial. So far, so good. This is just purely algebraic manipulation and reassembly of terms. When we put it back into the inclusion-exclusion formula, now something interesting and deep starts to arise. Each of the inclusion-exclusion sums now has the form of a power over a factorial. We reassemble terms and we find on the right a sum which looks like an exponential. It's the old adage again. If it walks like a duck, if it quacks like a duck, it's got to be a duck. If it walks like an exponential, if it quacks like an exponential, it's got to be an exponential. That sum is an approximation to an exponential function. In fact, it's a truncated exponential series whose parameter is minus lambda. And so, without further ado, we find a beautiful approximation, a Poisson approximation emerging out of the ruins. Accidental? Not so hasty. What was at the heart of this discovery? Right? All of this was just algebraic manipulation. And something beautiful and unexpected dropped into our laps. We should surely look back and ask, where did this come from? Was it purely accidental? And when we trace it back, we discover that this progression was permitted because the inclusion-exclusion sums had a particular character. The inclusion-exclusion sums were of the form of a power divided by a factorial. And whence the power? Of course, the power arises. It's a product. It arises because of an underlying independence. This was a bounty of independence. And this was at the heart of the Poisson approximation to the binomial. The independent trials engendered products, and that led to the inclusion-exclusion sums being powers over factorials. And the moment you had that, the rest was just simple algebraic calculus, just chugging through the motions, as it were, and out comes an exponential. This leads us now to suspect that the Poisson discovery was not merely accidental, that the Poisson is waiting to be discovered the moment we have events which are independent or perhaps only approximately independent. And this now essentially gives us a beautiful theorem which gives us a Poisson sieve. So let's write down what a discovery is. What we're going to do now is move into a generic framework where we have a system of events A1 through AN. Think of them as bad events, rare events. Fortunately, these bad things happen rarely. Bad things happen to good people only very, very occasionally. So these are the bad events. We're going to think of these as going to be perhaps not independent, but perhaps approximately independent, where the level of dependency is not strong. If that is the case, then we could hope for a power over a factorial to emerge for the inclusion-exclusion sums. At the moment you do that, everything else will carry through without change in toto. So, the key here is a bounty of independence, that inclusion-exclusion sums look like the powers of a fixed quantity divided by a factorial. The power is going to rise because the probability of an intersection of things which are nearly independent should be a power, should be a product. And if that is the case, the entire argument just carries through. The number of bad events that occur, the number of rare events that occur, is governed by a Poisson law. And the expectation of that Poisson is exactly the parameter lambda which is appearing in that power. And in particular, the probability that no bad events happen, a fortiori, is given by simply an exponential with exponent minus lambda. You see now the prominence of where this idea that this is actually a sieve is appearing. We have a lot of events n, a lot of trials, if you will, which are not perhaps independent, but close to being independent. The level of dependency is small in some formal sense. Given a large number of bad events, how many bad events actually occur? Well, governed by the fixed parameter lambda. And therefore, what we're really doing is metaphorically straining through a collection of bad events and happening to catch a few. This is the idea, the metaphorical idea of a sieve. What we have discovered is a very delicate Poisson sieve for the problem. Of course, this is the formal trappings of the problem, as it were. Okay? But a slogan is always nice to have because it captures for us the essence of a mathematical theorem, without, of course, a great deal of precision. So, promptly, here is a slogan. The number of bad events or rare events that occur is generically governed by a Poisson law.